Hey everybody, and welcome to a video on accuracy arguments. Recall that last time we shifted our focus from having developed probability theory to asking some questions about probability theory as it relates to our goals in this course. So we asked, is probability theory a good scientific inductive logic, right? And there were really two questions we could break this down into. First, can we rationally justify probability theory? And secondly, to what extent does probability theory give us what we wanted out of a scientific inductive logic? And last time, we focused on the first question, right? Can we rationally justify probability theory? And we're going to continue to focus on that question in this video, and next week we'll turn to the second question. So there's two main attempts that we're going to look at to assess whether we can rationally justify probability theory. There are others we could look at too, but these two are particularly prominent attempts. First was Dutch book arguments, which we looked at last time. And remember that according to a Dutch book argument, having degrees of belief that are not probabilities, that is, degrees of belief that don't satisfy the probability axioms, is irrational because it licenses senseless behavior, in particular, senseless betting behavior. There will be sets of bets that are credences or degrees of belief will license as fair for us to take, and yet when we jointly take all of them, we're guaranteed to lose money. Right? We suffer a Dutch book. And this suggests that the degrees of belief in question, the degrees of belief licensing this behavior, are irrational. Right? Today we're going to look at a different vein of arguments that attempt to justify probability theory, and those are accuracy arguments. Now, according to accuracy arguments, having degrees of belief that are not probabilities is irrational because such beliefs are guaranteed to be less accurate than some other probabilistic belief state. So here we're not thinking about the rationality of behavior that's licensed by the beliefs in question or betting behavior. We're thinking about just the accuracy of the beliefs in question. So if we were to state the accuracy argument for the probability axioms in a general way, we could say that credences that are accuracy dominated are irrational. And by accuracy dominated, which we'll go into in another slide, we mean credences that are guaranteed to be less accurate than other possible credences we could have, come what may. Right? So we suppose that credences that are accuracy dominated are irrational. Second premise, credences that violate the probability axioms are in fact accuracy dominated. That is, there are other credence functions that will be guaranteed to be more accurate than them. Thus, we conclude that credences that violate the probability axioms are irrational. And of course, there's a converse to this argument too, where we can argue that credences that satisfy the probability axioms, that is, that count as probability functions, are not accuracy dominated by any other possible credence functions. So this then provides an argument for the probability axioms. And there are similar arguments that we could introduce for things like the ratio rule or updating by conditionalization. They introduce, again, some more subtleties like they did in the case of the Dutch book arguments, so we won't go over them, but they do exist. So we'll get the general structure of these arguments by looking at them in the context of the original probability axioms, right? Normality, non-negativity, and additivity, but there are versions of these arguments that can also be used to justify some of the other principles that we've been employing. Okay, so we're talking about accuracy. So how are we going to measure accuracy? Well, recall from earlier in the course that one common way to measure the accuracy or inaccuracy of a set of credences is to employ the Breyer score. So if you want more detail on the Breyer score, you can go back to the video that we had on the Breyer score. I think it was in week 4 that we looked at it, possibly in week 3, but there's an earlier video on the Breyer score. We'll recall what it is briefly here, right? So I'm going to use this TV function to represent a truth value function. So it takes as input propositions or statements and outputs 1 if the proposition in question is true and 0 if the proposition in question is false, right? So TV is just a truth value function. Now, the inaccuracy of a credence function C, defined on a set of finite set of propositions, x1 through xn, is given by this I function here. Basically what we do is we look at the squared difference between the credence we assign to a proposition x and the truth value of x, right? And that's intuitively, right, our accuracy or inaccuracy with respect to that particular proposition, right? How far are we from the truth value of that proposition? So we're better off, we're more accurate, right, if we're closer to the truth value of the proposition, less accurate if we're further from the truth value of the proposition. And then we add up all of those individual inaccuracies for all the different propositions we have beliefs about, and we get our total or sum inaccuracy. And this prior score, you recall, you want it to be low, right? If it's low, you're more accurate, right? If it's high, you're less accurate. So it's measuring inaccuracy, right? A higher Brier score means you're more inaccurate. So let's look at a simple example of computing a Brier score for a particular credence function. So suppose that there's three propositions that you have beliefs about, x1, x2, and x3, right? Suppose that you spread your credences this, right? You assign 1/3 probability to each of these propositions, and suppose the truth value of the first ends up being 1, so the first proposition, x1, ends up being true, the second two end up being false, right? Then, right, we can compute your overall inaccuracy by looking at, right, the difference between your belief in each of these three propositions and its actual truth value, squaring those and adding them all up. So in this case, right, your degree of belief is 1/3 in each of them. And so in the first case, we look at the difference between 1/3 and the truth value of x1, which is 1. So 1/3 minus 1, square it. And then in the second two cases, we look at the difference between your credence in x2 and x3 and the truth values of those propositions, which are 0. So we get 1/3 minus 0 squared and then 1/3 minus 0 squared. And if we add all those up, we get 2/3 as the overall inaccuracy of this particular credence function. Okay, so that's how to use the Brier score to compute the accuracy or inaccuracy of a particular credence function. Remember, you want your Brier score to be low, right? If you were perfect, right? If you're perfectly omniscient, if you assigned 1 to all the credence 1 to all the propositions that were true, and credence 0 to all the propositions that were false, then you'd have the best Brier score you could possibly have, right? You'd have a Brier score of 0. You'd have no inaccuracy. Okay, so now we introduce the notion of accuracy dominance. So we say that one credence function A is accuracy dominated by another B, just in case given any coherent truth value function, right? The Brier score of A is greater than that of B, right? So no matter what the truth values of our atomic propositions end up being, no matter how the world ends up turning out, A is going to have a higher Brier score, but it's going to be less accurate than B, right? So this means, right, that no matter what the truth values of the propositions in question are, A is guaranteed to be less accurate than B. So I'm totally right, B is going to be a better credence function to have in this circumstance. Okay, so here's a very simple example of accuracy dominance. Suppose I just have beliefs about one proposition, x, and I assign credence 1.5 to it. Right? So this is clearly a crazy credence to assign to it because it's above 1. Right? This is going to be accuracy dominated by a credence function that assigns to the proposition x credence 1. Right? Let's see how this is. Well, right, let's measure the inaccuracy of each of these credence functions. Now, there's two different cases, right? Because it might be that x is true or it might be that x is false, right? That is, the truth value of x might be 1 or the truth value of x might be 0, right? So we can compute the inaccuracy of C and of C star in each of those two cases, right? So we compute the inaccuracy of C, and we see it's either 0.25 if x is true, or it's 2.25 if x is false, right? Then we compute the inaccuracy of C star, and we see that it's 0 if x is true, right? And it's 1 if x is false, right? In either case, right, if x is true, right, then we go from having inaccuracy in the case of C being 0.25 to only being 0 in the case of C star. And if x is false, then we go from having inaccuracy of 2.25 to having inaccuracy of 1, right? So no matter whether x is true or false, C star is going to be a more accurate credence function than C, right? So this tells us you should never assign credences that are above 1, right, to a proposition. And similarly, right, this is going to motivate an argument for normality and an argument for non-negativity, right? You should never assign negative numbers to any propositions as your credences. And you have to assign probability 1 to a tautology that's guaranteed to be true, right? So it's fairly straightforward to see how those arguments would go for normality and non-negativity. That if you have a credence function that's that assigns negative numbers to different propositions, or one that fails to assign one to a tautology, there's going to be another credence function we can come up with that's going to accuracy dominate those credences. The argument for additivity, though, is a bit more advanced. So we actually won't state it here, but we can suggest a more direct accuracy arguments for at least one of the probability rules, the negation rule, which recall, right, is a consequence of additivity together with the other axioms. So, and this will suggest how, right, the argument for additivity could go. It's just that the argument for additivity is going to be a more complicated argument. Okay. So, suppose we have a proposition P and its negation not P. Now this square here, right, represents different credences we could assign to P and not P. And I'm going to assume we just assign credences between 0 and 1 because we've already sort of ruled out the cases where you assign credences that are negative or that are greater than 1 because you know that in those cases you're going to be accuracy dominated. So this square here, this unit square, represents different credences you could assign to P and to its negation not P. Right? Now note that there's really 2 points in this space that correspond to possible worlds, to different ways the world could be. It could be, right, that P is true and not P is false. So that would be the upper left-hand corner. Or it could be that not P is true and P is false. That would be the lower right-hand corner, right? Those are the 2 possible ways the world could be, right? And what negation rule requires is that we assign our credences to P and not P in such a way that they fall along the line that connects these 2 possible ways the world could be, right? So we're allowed to have, for example, credence 0.5 in P and 0.5 in not P, or I could have 1 in P and 0 in not P, or 1 in not P and 0 in P, right? Or any combination of numbers to P, assignments of numbers to P and not P, such that together they add up to 1, right? That's what negation rule requires, right? So negation rule allows me to have credences that go along this line stretching between 1, 0 and 0, 1, those 2 points in this space. Now suppose that I had credences that violated the negation rule. Maybe I assigned low credence to P and also low credence to not P, so that the probability I assigned to both of them together doesn't add up to 1. Right? So maybe I'm at where this x is on the in the square. Right? Then I claim my credences are accuracy dominated by another possible credence function I could adopt. Right? Namely, right, if you project this point onto the line of credence functions that satisfy the negation rule, you'll get a point that's guaranteed to be more accurate than the one that's off the line. Right? We can think of, right, Breyer's score is measuring Euclidean distance between points in this space, right? The point that's on the line, right, is going to be closer to both, right, the point 1, 0 and to the point 0, 1. So regardless of whether P ends up being true and not P false, or not P ends up being true and P false, right, the point on the line is going to have a lower Breyer score. It's going to be more accurate than the point that's off the line, right? So this suggests that any credence function that violates the negation rule is going to be accuracy dominated by one that satisfies the negation rule. And we could come up with a similar argument for additivity in general. It's going to be more complicated, though, because it's going to involve more dimensions, because we have to consider 3 different propositions, A, B, and their disjunction, right, A or B. So we'd have to move into a 3-dimensional space to make a similar sort of geometric argument. But the argument is similar for the additivity principle. Okay, so hopefully this gives you at least some idea of that. Okay, so then what have we accomplished, assuming that we get our accuracy argument for additivity as well as for normality and non-negativity? Well, we then have the credences that violate the probability axioms are accuracy dominated, while I think probability functions, that is, functions that satisfy the probability axioms, are not, right? If we go back to this point, right, any point along this line of that satisfies the negation rule is not going to be accuracy dominated by any other point, right? Because it's either going to be closer to one of the possible worlds or closer to the other one. Okay. So, then coupled with the Dutch book arguments, this provides some rational support, at least, for the foundations of probability theory, for those axioms, and hence for the rest of probability theory that we derived from those axioms. Right? So now we've tried to answer that first question of whether we can rationally justify probability theory, and we've at least, I think, made some good progress towards that via the Dutch book arguments and the accuracy arguments. Now we have to look at how much probability theory can deliver us as an inductive logic. How much does it give us of what we were originally seeking in terms of a scientific inductive logic? And that's what we'll look at in our final week next week. For this week, just remember to complete the participation poll for this video, and I'll see you guys next time. Thanks so much.